Welcome to separable equations. So definition, separable first order equation can be written in the form h of y prime is equal to f of x. So just a quick note, if it is in this form, then use substitution applies, or the chain rule applies essentially. So note, if we take the integral of h of y prime dx, this should be equal to the integral of f of x dx. And then we could apply use substitution essentially, right? So note that dy would be y prime times dx. And so what we really essentially have is we can integrate the left side with respect to y and just integrate h of y dy. And on the right side, integrate f of x dx. We've already done this briefly. We saw this earlier when we were doing linear differential equations. So again, recall that if we had y prime over y equaling negative p of x, that this just became natural log absolute value of y was equal to negative p of x plus c. Doing that, we are using this rule, integral of negative. I lost my integral sign on the right. This should be negative integral p of x and then dx plus c. So we are here doing precisely what the note says we could do. To get from y prime over y, we essentially were integrating, and we could change it to just integrating 1 over y. So let's go ahead and do some quick examples. So the first one, let's find the general solution to y prime minus 3x squared y squared is equal to 2y squared. So if we rearrange this, this says that y prime is equal to 3x squared y squared plus 2y squared. Then we can factor out a copy of y squared from the right. We are looking at y prime is equal to 3x squared plus 2. Sorry, y prime is equal to y squared times 3x squared plus 2. Or y prime over y squared is equal to 3x squared plus 2. So at this point, this is in the format we were looking for. So this is in the form h of y times y prime is equal to f of x. We can then solve this. If we integrate both sides, this becomes the integral of 1 over y squared dy is equal to the integral of 3x squared plus 2 dx. Again, that's sort of me applying my use substitution to put the left integral in terms of y instead of x. At this point, we can integrate that left side, integral of 1 over y squared dy. We are looking at a negative 1 over y. On the right-hand side, we would have x cubed plus 2x plus c. We could rearrange this so that we have a flat y equals. This is equivalent to saying that y is equal to negative 1 over x cubed plus 2x plus c. Next up, let's go ahead and solve the IVP. Y times y prime is equal to x squared times y squared minus 2, with y of 1 equal to 4. So first thing we need to do is get this into the general form for separable equations. If we divide through by y squared minus 2, we have y times y prime divided by y squared minus 2 is equal to x squared. This is in the desired format of h of y times y prime is equal to f of x. So we can go ahead and integrate. You get that the integral of y over y squared minus 2 dy is equal to the integral of x squared dx. The left-hand side, we could do some form of u substitution. If we set u equals to y squared minus 2, then we would have du would be 2y dy. We have a y dy in there, so we have y times dy is equal to 1/2 du. So on the left-hand side, we would have the integral of 1/2 times the integral of 1 over u du is equal to the integral of x squared dx. So we have 1/2 times the natural log of the absolute value of u is equal to 1/3 x cubed plus c. Plugging back in our u, we have 1/2 times the natural log of the absolute value of y squared minus 2 is equal to 1/3 x cubed plus c. We could theoretically rearrange this and sort of solve for y, not completely, but we don't necessarily have to. So now if I have the initial condition y of 1 is equal to 4, we have 1/2 times the natural log of 4 squared minus 2 is equal to 1/3 times 1 cubed plus c. So we have 1/2 times the natural log of 14 is equal to 1/3 plus c, or c is equal to 1/2 times the natural log of 14 minus 1/3. Putting this all together then, we have 1/2 times the natural log of the absolute value of y squared minus 2 is equal to 1/3 x cubed plus 1/2 times the natural log of 14 minus 1/3. So this is what is called an implicit solution. We have not solved exclusively for y. Okay. I should note that for here, we're finding our particular solution. That was when we plugged in our y of 1 equals 4. What we have here, this is our implicit general solution. So separable equations are nice in that you just have to know how to do the integration. There's not really any differential equations tricks we're using at this point, no variation of parameters. We're just breaking it up and performing two completely separate integrals. As we've seen, sometimes we get an equation that's explicitly in the form y equals, or can easily arrange the equation to that format, and sometimes is a little more complex. You're welcome to leave it in implicit form unless I say otherwise.